like in the evening, like around 4 or 5. Yeah, I have like a layover, like at JFK.
Yeah. Right, I think we can start with it.
Hi, all. Yeah. So I'm going to present our work, Differentiable Microscopy, a new paradigm for optical system design. So like this is a same work, but kind of extended version of the presentation that Dushan presented like in the CVPR rehearsal present thing. Like, yeah, if you were there. Okay. So yeah, so in this work, our what we try to achieve is like, can we use machine learning to like design new imaging designs, like new optical setups, so new microscopes. So what we want is like, uh, without giving anything, like can machine learning to figure out to do the task, or like to find the uh, correct correct optical setup to do some task. So first, uh, if I go back to the history, like there are like microscopes uh, invented in like different time points. So the first one is phase. Let me get my pointer. So this first one is phase contrast. Here, our goal is to kind of so we are given a particular complex field, electromagnetic field, and our goal is to kind of extract the phase of the field. And as example, like if we don't have phase contrast and we just like image the amplitude of the field, we get this one. And if we have the phase contrast, we get like higher contrast of the phase. And yeah, which has like more details if the sample is thin and transparent. And the second one is confocal, which is basically like, I will like go more detailed into these microscopes later in my presentation. So here the confocal is basically like we have a thick sample and we need to image a middle plane of that sample. So if I try to do like wide field or something kind of like that, we get a lot of scattering, or like a lot of out of focus light comes from other planes of the thick sample. So we get this kind of image if we do not have this confocal principle. But if we have the confocal microscopy, we get this sharp, nice looking image, which is exactly the uh, a middle plane of the thick sample. And the third one is super resolution. Here, the idea is like we want to go higher than diffractive limit to image the sample. Yeah. So the problem of like these kind of approaches to discover microscopes are like, as example, like let's say this one is the paper uh, by Senike regarding the phase contrast invention, and yeah. So this takes like this is published in 1932, but it is kind of he began to work on this 1920. So like there is like decades of year gap between like the actual invention and the start of that work. So what this says is like it takes like really long time to invent microscopes. So what if we can use machine learning to invent microscopes? So then we do not have to wait this much of like long time scales. And yeah, so how machine learning have been used for this paradigm? Mainly, like there are sufficiently like a lot of works that use machine learning to tune parameters of the existing microscopes. As example, what we can do is like we can kind of uh, model the computational setup of a particular microscope, and we can like in a differentiable manner, of course, and then we can we can kind of try to optimize different parameters of that setup. But the problem is like to do that, we need to know the microscope. We need to know the theory of the microscope so that we can model it in a computer and then we can optimize things inside that computational setup. So yeah. So the problem we are asking is like this machine, like this current works cannot derive new microscopes because they need existing computational designs. So we need a method to parameterize the microscope in a general way. So if we have a general way of microscope parameterization, then we can learn the microscope without specifying details of what the microscope should be. And yeah, so how we can do that? We can over parameterize the optical designs and yeah, let the optimizer to do the magic. But I will I will go through what this over parameterization means and why it should work. Yeah. So this is similar to like what we do in computer vision domain where we have like large models instead of like handcrafted things. As example, let's say like for the edge detection, we have a canny edge detector, which is like very handcrafted way of doing edge detection. But on the other hand, we can do like like convolution network to do that, and which is our parameterized design. Okay, so yeah, from here onwards, like content will be different compared to the previous presentation from Dushan. So first, we need to like see why over parameterization. So let's consider a very simple problem. Yeah, this is the problem. So the idea is we have a lens and we put we put something in some distance, is it? And then we need to get a kind of flipped version of that same object. Yeah, in the output plane, which is like located from z distance from the lens. So our goal is to find the focal length of the lens such a way that yeah, this flipped version of the object will be reconstructed at the output. So we all know that like for there is a like definite solution to this problem. It should be like z/2. Yeah. So when f is z/2, we can if we have like this QWT image as the input, we get this type of like flipped image at the output. So the direct way to solve this, not the direct way, but like to solve this using machine learning, what we can do is like we can model this small computational setup in our computer, and then in a differentiable manner, and we can kind of try to optimize the focal length of the lens such a way that the input will be reconstructed at the output in a flipped manner. But there is a problem. So since this is like one variable optimization, we can model the loss landscape because we only optimize the focal length, right? So this is like L1 loss between flipped input and the output. So you can see like this is the optimal point, the red dotted line, and you can see the loss landscape is like it has like really high frequency fluctuations. So a gradient based optimizer cannot travel through this space. So yeah, that's it. Yeah. So basically what happened if I try to learn this like focal length using like, so what we do here is like we model this and we have a loss function. It is this one, and we have a parameters to learn, which is the focal length, and we try to optimize the focal length to reduce the loss. And what happens is, yeah, nothing happens basically. We cannot learn it at all, and the loss model doesn't converge. The reason is this like very high fluctuations in the loss landscape. So what we can do here then? So one way to do the over-parameterization for this case is we can just replace that lens with the diffractive layer. What is diffractive layer? I will like go into detail. So let's say like this is the lens, or like this is yeah, this is the, let's say this is the lens, and E in is the input electric field just before the lens, and E out is the electromagnetic field just after the lens. And this lens basically like do a transformation, which is basically A, and this one is like element-wise product. So yeah, let's say like for the ideal lens, we have this type of transformation, uh, which is basically like it is basically a phase distribution. Yeah, and it is a complex transformation. Only change happens will be to the phase of the input light field, and there is F here, and that is the focal length. And we know that the ideal focal length will be Z/2. So our goal is to kind of optimize this thing and it should give ideally this F star. So if I kind of like visualize this phase part of the transformation, we get something like this. So yeah, so this image is without like this J part, and yeah, it gives this kind of thing. And this is basically like without any parameterization. We have to learn the F inside here. So how we do the O parameterization? What we can do is like we can replace this entire thing with capital B, which is a phase mass basically. So you can see like here the focal length is just like one dimensional variable, and this one is like n by n dimensional variable. So there are a lot of parameters there. So yeah, so we are trying to learn all n squared variables here. So that's how O parameterization comes to play. So yeah, so what this does. So I will go to the like previous example, and if we use the O parameterization, yeah, the losses like reduce very smoothly, and it gives our expected results. And then yeah, let's look at the results. So these are the results from the image plane, and you can see like this one is the flipped version of the input, and the first and second rows shows the amplitude and the phase of the electromagnetic field at the image plane. And so the first column is basically like what happened when we put random phase distribution at the lens location. And the second one is like it is the ideal actual lens with the expected focal length. And the third column is like what we got from the optimization, which is basically our parameterized design. And you can see like the reconstruction wise, yeah, the learned one clearly like learned to reconstruct the flipped version of the input. And if we consider like the phase, like here our loss doesn't have any phase component. What we try to do is kind of try to reconstruct the amplitude of the field, right? As example, like we have an input field, which is QWT image, and our goal is to reconstruct the flipped version of the input at the output. So we only consider the amplitude of the field. We don't care about what the phase distribution looks like. So that's why these two are different, and we don't care about that. So what it learned like actually in the phase distribution. So these are the phase distributions it learned, and yeah, I know like you cannot see like much for these two. So this one is the random phase distribution, and this one is the learned or parameterized distribution, and this one is the lens, which I showed previously. Yeah. So
in that case, like what are the values of these colors?
Yeah. So I haven't put the scales here, but these are like unfolded. I have like yeah. So I have this to show the like mod 2 pi values as well. So like yeah. So this mod 2 pi values ranges from 0 to 2 pi, and these are ranges from like different. Yeah, they are in different scales. Yeah. Is it good solution to
I
some?
think like you might need to zoom in or like see actual values
Yeah,
because
yes.
this.
Yes, yeah, we cannot see anything here, but yeah. So that's why I put this slide. So
But what is the
yes,
range of the values like?
so
It
yeah,
is
this the value range is 0 to 2 pi because yeah, there is like v mod by 2 pi. So the yeah, I think I might have to like put a color map there, but yeah, usually like it is the dark blue color is 0 and a yellowish will be the 2 pi. And yeah, so this ranges from 0 to 2 pi, and what we can like this last row is basically like the zoomed version of the center part of the feed, and that is what zoomed here. And yeah, what we can observe is like in this over parameterized design, we have like some sort of features that are like similar to the lens, but you can see like they are not like, so in the lens like it is kind of distributed in a like very symmetrical manner because it is a lens, but here since it has the flexibility it learned like uh, different things in different parts. Yeah, and the thing is like it actually like makes the loss even smaller than the ideal lens. uh, so yeah, so now what we can do is like we can kind of dissect these models and sorry, yes Nisha.
Yeah, so but this was like trained on only one image, right? So the optimization runs on only the QWT image. And I think
Yes,
the difference is the lens is a general solution that works for any image. How do
yeah,
we
so yeah,
this
so
solution fitted for the.
yeah, I seen, even though I haven't like included any images to this, I have tested this design, like this particular design on like untrained data sets as well. As example, like I tested on MNIST data, and it worked for even though like so right now, as you mentioned, like the model is only trained on QWT, that one image, but it worked for all the MNIST images as well. Well, but I might need to like check other like more complex image distributions as well. But yeah, generally I think it is general.
Mhm.
Uh yes. And yeah, so then we want to check like whether why these whole parameterized models converge easily. Basically, what we want to look is like how this high dimensional loss landscape looks like around this lens, uh, around this like lens phase distribution and around this learned or parameterized phase distribution. So to visualize that, so basically like we cannot visualize, right? Because like it is very high dimensional, like in squared space, so we cannot visualize the loss landscape. But like there are some previous works which works on, yeah, that kind of worked around this problem, and they have this method. Yeah, it is like not nothing like fancy, but so let's say like we have this loss landscape which has like theta 1, theta 2 uh, learned parameters, and L theta is the loss. And what we do is like we have this theta star, which we found. So this theta is basically the parameters, the learnable parameters. And the theta star is like, let's say, the optimal value we found. It can be lens phase distribution, or it can be learned over parameterized design. So what they do is like they kind of sample different random weight weight sets, and then they kind of like get the cross section and kind of project the loss here. So if we do this like multiple times with multiple theta randoms, so then we can kind of get multiple loss, like multiple like this 2D type of loss landscapes, right? So if I like kind of look bunch of them, then I can get like a good understanding about like how the loss uh, fluctuates around this optimal point. Because when I change the theta random, it goes, this line goes to like different locations, but this theta star is like constant. So like we basically like cut the loss landscape in a different ways. But all these ways includes theta star. Yeah. So this is the basic law parameter. This is the parameterization we use with this alpha parameter. So you can see this when alpha equals 0, theta will be theta star, which means this point. And yeah, and I change basically alpha minus 4 to 4 with where like there is 800 like samples in between alpha samples. And yeah, this is what the loss landscapes look like. So the first case, alpha 0 means the lens with optimal. So yeah, the first diagram, the alpha equals 0 means the lens with the optimal f. And the second one, alpha equals 0 means our learned or parameterized design. So what we can see is like you can see the really high like fluctuations they are around the lens with optimal f, but in contrast, the fluctuations are really like very low frequency around the learned or parameters design. So there are like conclusions. There are few conclusions we can get from here. So the first one is like machine learning models are not very effective in designing these optical systems because, as we saw, there is usually like they have very highly non-convex loss landscapes. And so what overparameterization can do is it can make the problem of optical system design tractable using machine learning by like kind of giving suitable points with smooth loss landscapes. Yeah. So this is basically like the background of the work, but now like we're stepping to actual problem of designing microscopes. So now we covered why we need our parameterization, and then what we want is how we can do that. So there are like a major requirement to come up with better parameterization method. Basically, like what we need is like our parameterized optical design should be able to basically like model any microscope out there. So in order to do that, we need to ensure our design should be capable of mimicking any linear transformation, basically. Yeah. So So what we found is like there are a few mathematical papers out there that discuss this type of aspects, where specifically like let's say a system where like let's say a system which has a linear transformation A between the input complex field E in and the output complex field E out. And so this particular work basically like try to prove that we can decompose this any arbitrary linear optical transformation A into a set of diagonal matrices and like a multiplication of diagonal and circular matrices. So yeah. So we also can found there are like very close relationships with circular matrices and DFTs. So basically we can transform this into a form of DFTs, diagonal matrices, and DFTs. So this again, like we try to convert into physical setup using this type of optical design, where we have lens which do the Fourier transform, and we have a filter which is a diagonal. So yeah, one thing like this transformation is basically like 1D transformation, but this is kind of 2D if you want, like yeah. But the basic idea is like this filter can be like represent as if it is like flattened, it will be we can put it into the diagonal of the diagonal matrix. So basically what I am saying is like ideally this any arbitrary linear transformation can be represented in optical setup or physical setup, which has bunch of lenses and bunch of filters in between the lenses. But there is a problem here. So this needs like 2n minus 1 these elements, right? So as example, if we take a number of pixels in the field 256, yeah, we need like 511 filters. And if we take like number of pixels in the field like 2048, then it will be like more, yeah, it is really high number. So we have a hypothesis here. So our hypothesis is like, we don't want, like, let's say like we compare this with the microscope, right? So let's say like particular microscope mostly work with particular set of data sets or particular set of image distributions or sample distributions. In that way, we can say that our input and output spaces like distributions are limited. So our goal is to find a transformation between those two image distribution. So in that way, we hypothesize that there exists such transformation, or there exists such solution, which we can achieve without having this much of filters or like lenses. Yeah. So with that in mind, we will go to our optical design. So this is the optical design we are proposing. The idea is this basically like tagged lenses, and in between there are filters. So it is similar to like this equation here, where like this particular CDC will be represented by filter lens setup. And this has a number of parameters of 2 into n squared into capital N, where capital N is the number of filters and simple N is a number of pixels we consider in a field. So this particularly this filter is basically like phase distribution we talked about like in the previous like lens example, or it can like we can learn both phase and also the amplitude as well. Yeah. So we can like use this conceptual analogy to this setup. So like in computation we have a ResNet or like any computation model, which so I have like kind of so I put this input image from upwards and like weights. So what I have done is like I kind of like make the weights as input to the model and keep the input images as a like side thing here. So what we do is like for a particular weights, we can use like particular weights to represent object detection or object classification or semantic segmentation, but using like same model or like at least same backbone of the model. So similar, yeah, there are like parallels to that. So as example, like we can have like different filters with same sample distribution to mimic different microscopes basically. Yeah. And yeah, we can have like other analogy as well like this. So yeah, this is, yeah, the idea is like, so we design this like filters as a like objects, right? So we can kind of like input into we can kind of like put those filters into our optical setup. So it is kind of like putting a CD to a CD player and watching different films. So similar to that, we can kind of put in different filters into the optical system to get different outputs of a given sample. And yeah, so these are like exact steps of the setup. So we have simulated object and we set up our optical system as a black box, and I will like go into this black box more detailed in the next slides. And we have decided imaging measurements. So the idea is we first model this optical setup as a differentiable function, and then we define the task and inputs and outputs. And then we simulate the data sets of input-output pairs. And then we define a loss function and we optimize the model and after we get the optimal parameters, we can design them and create the microscope. So this is the black box look like basically. So what we see is like we see like this any microscope setup generally like is basically a cascaded system of 3 blocks: illumination optics, specimen light interaction, and imaging optics. So what we do is we model this illumination and imaging optics using the proposed parameterized setup that I discussed in previous slides. And then this specimen light interaction is basically depends on the task or goal that we want to achieve. So that's why it is a general framework to do, to mimic ideally any microscope. So yeah, let's look at some results. So first one is confocal imaging. So here the standard confocal setup. So our goal is to our goal is we have a thick sample and we need to image a middle slice of the sample. As example, like here is the sample and this dark green slice is what we want at the image plane. So yeah. So in the coherent microscope, we image one point at a time. So the idea is like this like dark yellowish color light shows like the input beam, and it basically like focus on this particular point. And the reflected light comes from that point will be then goes into this pinhole, and that pinhole basically like remove the light comes from the other places of this like cone. And yeah, if we use detector and detect this pixel, it should be like, yeah, it will be similar to this particular point. The value will be similar to that particular point. And this figure I showed like how the illumination field looks like immediately before each plane of the sample. So here, this is the middle plane. The field immediately before the middle plane of the sample, and you can see like it is like focused here. And this one is basically like right here. Maybe this one is right here. So for this demonstration, we use like a sample with like 5 layers. Yeah. So this is like how.
One comment is like, so coherent doesn't mean that it's point scanning. It's a different.
Sorry.
The coherent doesn't mean that. So coherent setup doesn't mean that it's a point scanning setup. So coherent and incoherence are different concepts versus point scanning and like wide field. So you can have wide field setups of incoherent or like point scanning setup with incoherent, and same goes for coherent. So coherent just means that the light is spatially or temporally coherent.
And yeah, thank you. So yeah, so this is like an example input output for the system. So this sample basically like shows like 5 slices of the sample, and as example, this is Z1, Z2, Z3, Z4, Z5. Yeah, they are kind of located in that order. And our goal is to get this particular plane at the output. And this is what we get from the confocal setup. So this is as Dushan mentioned, like this is a point scanning setup, which basically means is like at a one time we only image one point, and we have to like move the entire setup across the sample, or we have to move the sample to image like the entire field, and we get this type of output, and which is more or less similar to the middle plane of the sample, and the setup basically like removes the light comes from these other planes. So yeah, it basically do the job, but there are like few artifacts also there. Yeah. So what we do is like we have this our general optical setup, and we use our proposed over parameterization model to model the illumination optics and also imaging optics. And for the specimen light interaction, so yeah, this is what specimen light beam, which is like in general the illumination optics, and then it kind of intercepts with the sample, and so the reflected light will be, we have a mirror also there. Reflected light will be fed into the imaging optics. So that is basically the specimen light interaction that is specific to mimicking confocal effect. And so this is the complete setup basically. We have this uniform illumination, which is a general illumination source. And we have this input illumination optics. And then we have a specimen light interaction. And then we have imaging optics. And this B1 or F5 or BI block basically is a one block of our proposed or parameters setup, which has two lenses and two filters. And this is example example specimen with 5 planes. And our goal is to kind of reconstruct the middle plane. So this is like how training looks like. And so here our goal is to kind of use this model to for the like real confocal data sets, right? But also what we want is a general solution for the confocal. In that way, our goal is to train this setup with synthetic data set, and we want to try it with actual data sets. So in that way, these are our training data set looks like. So our training data set has like 2 sub data sets. The first one is MNIST, and the second one is this synthetic beads. So these both two are synthetic data sets. And these are like 2 examples of those particular sub data sets. And yeah, so for this particular sample, we have ground truth, something like this, which is this like middle part. Yeah. And our prediction, like it should ideally look like this. And for the for the MNIST data, we have a ground truth like this, and predicted one ideally should look like this. And our goal, so we calculate. So this I predict basically what we get from this I predict we obtain at the detector, and we calculate the loss between the ground truth and the predicted. Yeah. And then we kind of like train all the parameters in the imaging optics and the illumination optics. Yeah. So after training the model, we can test it with with large images as well, because for the training we use like simple like small images, but at the testing we can like test with large images within like that are from any distribution. So as example, this is a test set. The test set basically consists of confocal images, and these confocal images like a model haven't seen these images in the training at all. And what we obtain is like this one is ours. So if I model like simple wide field imaging setup, we get something like this. It has like all the scattering and all the like out of focus right there. And this one is the confocal results, which I showed in the previous slide. And this one is what we obtain. and yeah, clearly it was like able to kind of isolate the middle plane of the thick sample. And this one is the ground truth, but we should like note that this one is like not visible. It is just a hypothetical ground truth, which is actually there inside that plane. What we get is something like this confocal output. So this our one should be directly compared with confocal. Yeah.
So the one question, if you go back, so your like our one looks better, right? In the confocal results.
Yes.
Have you tried confocal is like one. So confocal also has some parameters, right? The design you can parameterize a confocal one, and it has like this. For example, the size of the pinhole will define like how much light comes in and
Yes.
how much background comes in, right? Have you tried to optimize the pinhole size and maybe it will become like?
Yes. Yeah, I specifically I tried. I did a grid search for like different pinholes, and this is the best results. Uh, I I I obtained with like different pinholes, but I think I might have to like do some experiments for the input illumination part, because currently I use like the, as I remember, I just like use a field that can focus into the point source, but I didn't kind of, yeah. But in terms of pinhole, yeah, this is the best result I got for different pinhole sizes.
So the second question is like, so pinhole, like when you put a pinhole, it's a rule, right? So we know the rule, like if you put a pinhole, it rejects the out of focus light, lot of out of focus light, and most of the in focus light pass through because of the geometry. You can even do it in geometrical optics and see like the light, how the light kind of like pass through, and there is a rule, right? So if you're saying like actually this our case is better, and if it is general, like it might have a secondary like rule that helps us generate better ones, right?
Okay.
Which I don't think, but like it might worth investigating why you have better results.
Okay, yeah, that makes sense. Yes. So what you mean is like on top of pinhole, we can add some other features to make it better.
I don't know. I don't think like you can make the pinhole better. I think the pinhole is sort of like it's been there for a long time, like 50 years or more. So, so I think like it's almost probably like the only route. The only other thing I can think of is basically like the interference playing some role. So you can probably generate like destructive interference for the background because people usually use confocal for incoherent imaging where the interference do not play a role. But here, which is we are modeling a coherent setup, so interference might also play a role.
Okay.
Yeah, so I think that is probably worth like thinking about. Can you use, for an example, different inputs types to kind of like interpret the model better and see whether you can figure out the rule.
Okay.
Yeah, if you can figure out the rule, I think like it makes it, it gives another dimensionality to this work. Whereas these models are not interpretable right now, right?
Yes.
And they are similar to like neural networks which we cannot interpret what the filters are doing. Whereas an edge detector, for an example, we can interpret what the edge detector is doing.
Yeah.
Yeah, and the other thing is about the efficiency. So I think like there is another group of confocal like setups where you can make the pinhole in a certain way, but then very small amount of light passes through, even from the in focus plane. And but the contrast becomes better and better with that. So do you know like what is the efficiency between this confocal and your confocal? Like,
yes. I think I checked that, but I currently don't remember, but yeah.
Yeah.
Yes. I as I remember the confocal, yeah, it is like more power efficient than ours. Uh, yeah, I think it is like uh, less than order of magnitude, but yeah.
Yeah.
Okay. Shall I move?
Yeah. Good.
So these are the results it learned. So these are the filters it learned. So what we can observe is like, uh, yeah. So if I like visualize the illumination fields learned just before the sample, we can see this kind of pattern. And if I like need to compare it with the confocal microscopy fields immediately before the sample, you can see like it has learned some aspects of like focusing light to a middle point, like center of the middle plane. Yeah. And also like if I look into this imaging optics, we can see something like a pinhole there. But yeah, and it is in the image plane. So yes, so it might play a role of the pinhole. Yeah. So as a second example, I use quantitative phase imaging or the phase imaging setup. So here the idea is like we have a sample which has a phase with a lot of information, but the amplitude contain like very low contrast information. Basically, the sample is thin and transparent. So our goal is to get this phase into intensity at the detector. So we use a loss like this. Basically, like the output intensity which we obtain at the detector should be similar to phi in the input phase. And we should note that this setup do not have a general linear solution. As example, like we don't have a general linear solution uh, to convert phase to amplitude. So in that way, so our method should be uh, so the only way it has a solution is like if it is a data distribution dependent, then they might have a solution. But yeah. So for this case, we use like this type of setup, which is slightly advanced from the previous one, because like this has uh, skip connections. Yeah, which is basically like act similar to skip connection in ResNets and all the computation modes. Yeah. So these are like results we obtain. Currently, the filters we couldn't kind of uh, explain the filters, but these are our results. Yeah. And at this point, it is not that quantitative, but yeah. And as a third example, I will explain a bit about this depth of focus, extended depth of focus. So here, yeah, this part we are currently working on that. And so why we need depth of focus? As example, like let's say this particular jellyfish. So it has like these out of focus neurons, and we need to get all the neurons to a focus. And yeah, so as example, like so in a general like detector, what we obtain is like this kind of image where we have some neurons in focus and some out of focus. But what we need is all are in focus, this type of image. And so for this, we particularly use like very simple version of the generalized microscopy with just one filter, because uh, we want to like explain the filter as well in this particular case. So this is what we obtain, and it do a good job of like getting the out of focus into focus. And we also like observe that if we like increase the number of filters, this gets better. And this is the filter we learned. This is amplitude and this is the phase. And interestingly enough, like there is a very recent paper, 2023 March, which tried to do this application, and they found that optimal filter it should be like this. And yeah, our like learn filter has like some similarities with this filter. Yeah. So yeah, that are like all the things from this work. And Kipmini like mainly working on like designing these filters, and Ramit and Hasdu working on implementing like quantization and fabrication aspects of these designs. And as a summary, what we do is like, let's say, if we talk about classical microscope designs, what we try to do is like optimize parameters of that particular microscope. So we have a confocal microscope space, and we find the optimal parameters. And we have a phase microscope space like this. But here we have O-parameters design, which include all the microscopes, not all, but ideally all the microscopes inside the design space, confocal microscopes and phase microscopes. And our design is somewhere here, let's say, and we use like some optimization method to come up with the confocal microscope or like phase microscope. And the potential of this work is like, in similar way, we can go into like entirely new optimal microscopes as well for different like different tasks. And so the limitation of this approach is like this needs specifically designed, especially designed optical elements, as example like these face masks. So this is like one of our ongoing work, optical architecture search. Here, what we try to do is like the current problem, what we try to do is like we try to make the loss landscape smoother in that way, like these gradient based optimizers can travel through the landscape and find the optimal solution. In contrast, in this particular case, what we try to do is like we do not smoothen the loss landscape. Instead, we want to have a good algorithm that can traverse that sort of like very high frequency loss landscapes. So here the idea is basically like we try to come up with optimizer that can kind of combine different optical elements to create a microscope. So yeah, that will not include any specially designed optical elements. Rather, it includes like lenses, free propagation, and yeah, well-known things. And this is our team. Yeah, that's it.
Thank you. Did any questions? Most of us know this work.
When getting the like best pinhole size for the confocal, like in that slide, so is it done with respect to that ground truth image? Like,
sorry, can you repeat that again?
Like you mentioned, you do some grid search to find the best pinhole size for the confocal.
Yes.
Like to obtain a fair comparison, you sort of get the best confocal also. So in doing so, like what's the objective like when doing grid search?
Okay, so yeah, mostly the objective is like qualitative performance. It is not a quantitative measurement. I just like kind of visualize all things in a grid and just like eyeball what is like, mainly because like when the pinhole size changes, it like gets like really bad sometimes. So yeah, so it is not like very because like what I noted is like L1 OSSI, we cannot use that kind of measurement because like because mainly because like these like ranges and scales are like far different. So I want to find the best pinhole that generally gives a better looking image. Yeah.
Thank you.
Any other questions?